Okay, so if I graph y equals sine of x on the coordinate plane over the interval negative 4 pi to 4 pi in both directions, in x and y direction, and I want to find the graph of its inverse, remember that inverses switch the x and the y. So I'm going to write the equation x equals sine of y in order to get the inverse. And I'm going to change that to be blue. Okay, and now I can see that my sine curve here in red is going along the x-axis from its range of -1 to 1. Switching the x and the y creates this vertical sine wave, and it's hugging the y-axis, and its domain is -1 to 1 inclusive, and its range is all real numbers. So you can see how switching the x and y switched the domain and range. Now the sine of x, that curve is a function. It passes the vertical line test. But switching the x and the y to get x equals sine of y, that fails the vertical line test. So that is not an inverse. Now, in order to make this function an inverse, I would need to restrict the range here so that it stops at this turning point where the y is pi over 2, and here at negative pi over 2 for the y. If I can restrict my range from pi over 2 and negative pi over 2, then what's in that region would pass the vertical line test. So if I graph the expression y equals arcsine of x, so this, remember, arcsine is the inverse of sine, and then I'm going to change the color to black. We'll make it a little thicker so we can see it. And now if we look here in the center, well, maybe we make that dotted instead. There we go, that shows up a little better. So now if we look here in the center, notice that the arcsine of x is restricted automatically from that range of negative pi over 2 to pi over 2. If I hide x equals sine of y, there we can see that region of my inverse is the only thing that's sketched. So Desmos knows that the arcsine needs to be a function, and it restricts the range for us automatically so that we know just these values that pass the vertical line test. Those values are called principal values. Principal values have the restricted range so that the arcsine is a function and passes the vertical line test. So if we think about what quadrants these principal values live in, negative pi over 2 to pi over 2, that's quadrant 4, and negative pi over 2 to 0 is quadrant 4. From 0 to pi over 2, that's quadrant 1. So the principal values for the arcsine come from quadrants 4 and quadrant 1. Okay, so to summarize that information on the front of your notes booklet, the graph that we're looking at here is the arcsine of x, and its domain is between -1 and 1 inclusive. The range, so that it passes the vertical line test, is bound between negative pi over 2 and positive pi over 2. The 0 to pi over 2 values, those are principal values from quadrant 1. And then from 0 to negative pi over 2, those are the principal values from quadrant 4. And remember, sine is positive in quadrant 1 and negative in quadrant 4. So in example 1a, We want to evaluate the arcsine of 1/2 for all angles in radians, giving exact values only. And remember our acronym, all students take calculus. Sine is positive in quadrant 1, and it's positive in quadrant 2. So our two solutions for one revolution around the circle would be a quadrant 1 and quadrant 2 angle. Arcsine of 1/2 is asking us what angle in radians has a y-coordinate of 1/2, and that would be pi over 6 in quadrant 1, and it would be 5 pi over 6 in quadrant 2. We remember that from our study of the unit circle. But we want not just the one revolution around the circle answers, but all possible answers. So using our pi over 6 principal value, we can write an expression representing all of the coterminal angles to pi over 6. So that would be plus or minus k times one revolution around the circle of 2 pi, and that's when k is an element of the integers. And that would capture all of the first quadrant solutions to arcsine of 1/2. Now for second quadrant solutions, we'll need a separate expression. So 5 pi over 6 plus or minus k times 2 pi, again where k is an element of the integers, and those two expressions together represent all of the angles in radians for which the arcsine of 1/2 is evaluated. So it'll equal pi over 6 plus or minus k times 2 pi, 5 pi over 6 plus or minus k times 2 pi. Now in 1b, we're asked to solve this equation for sine of x plus 5 is equal to 2. And just like any linear equation, we'll start by moving terms to the other side of the equal sign to try to isolate the function sine of x. So subtracting 5 from both sides leaves 4 sine of x equals -3. And then we'll divide both sides by the coefficient on the function. And the 4's cancel. And we're left with the sine of x is equal to -3/4. Okay, to undo a sine, we need the arcsine. So x is equal to the arcsine of -3/4. And we're going to find the principal value using the calculator. And we're asked to be in degrees because we want our solutions over the interval 0 to 360. So we're going to change our calculator from radian to degree mode and evaluate the arcsine of -3/4. Rounding to 2 decimal places, that's -48.59 degrees, and that's our principal value. And we're going to use that principal value to find our solutions over the interval 0 to 360. So all students take calculus. Our principal value is -48.59. That's a quadrant 4 angle where sine is negative. And sine is also negative in quadrant 3. So our principal value is here in quadrant 4. To get within this interval 0 to 360, we're going to need to add 360 degrees to that principal value to get our quadrant 4 solution. So negative 48.59 plus 360 is 311.41 degrees. And that would be our quadrant 4 solution. Then to get into quadrant 3, this halfway around the circle would be 180 degrees, and we're trying to get counterclockwise forward into quadrant 3. Our principal value is negative, so we would be taking the principal value and subtracting that from 180, because minus a negative would be a positive. So this is 180 minus negative 48.59, which is 180 plus 48.59. And that will get us into quadrant 3. At 228.59 degrees. And we can check those answers in the calculator by substituting each in for the x. So 311.41 degrees plus 5, and then that's approximately 2, which checks with our original equation. And then we'll do that with our second solution, 228.59 degrees. And again, answer rounds to 2, which checks